In this video, we are going to talk about how to find the direction and magnitude of the magnetic field generated by a circular loop of current at some point along the central axis of the loop. Here I've labeled that point P. The loop is some distance, z naught, from the point horizontally, and the loop has a radius of big R. Now, from solving the Biot-Savart equation, you get an equation for the magnitude of the magnetic field, which is at the bottom of the screen here. It is mu naught I times r squared divided by 2 times r squared plus z naught squared, all to the 3 halves. Now, that comes from solving the integral in the Biot-Savart equation, which we have not done in this class, and I will not expect you to do. Your only job is to be able to use this equation where you know I, R, and Z naught in order to find the magnitude of the magnetic field. So what this video is going to be about is finding the direction of the magnetic field at point P, since given some I, R, and Z naught, we can find the magnitude of the magnetic field already. So in this loop, we are assuming that the loop is circulating in such a way that the current at the top of the loop is coming out of the board at us, and the current at the bottom of the loop is going into the board away from us. And what we're going to try to do is we are going to try to find the magnetic field components due to each of these two sections. Though hypothetically, we would need to do this for every possible section on the loop. We're only going to choose 2. So the basic idea is we're going to take our loop and we're going to split it up into little sections, right? So there's some little section at the top of the loop, DL1. There's some other section here, DL3, I'll call it. There's some little section at the bottom of the loop, DL2. And in order to find the total magnetic field, we would need to add up the contributions from all of these little sections throughout the entire loop, right? And this is what this would become an integral in our Biot-Savart equation, which I'll just write down here for reference. It is that the magnetic field equals mu naught I over 4 pi integral of dl cross r hat over r squared. So we would need to add up all of these little dl's around the entire loop because they're in our integral with the appropriate r hat and r squared for each of those little bits of current. We are not going to do that, but just as a reference here, my dl vector always points in the direction of the current at any given moment. So for example, dl1 points out of the board. At the top of my loop, the current is coming out of the board, so dl is coming out of the board. At the bottom of the page, dl2 is pointing into the board because that's the direction that the current is pointing. And when you actually do that integral around the entire loop, you end up with the equation above for the magnetic field magnitude. And if you take the cross product, you'll find the direction as well. What we are going to do is we are simply going to use the magnitude given, and we are going to try to find the direction by actually drawing out the direction of the magnetic field due to individual bits of the loop. So we're simply going to take DL1 at the top and DL2 at the bottom as being somewhat representative samples of the loop and try to find the magnetic field due to both of those components. Let's begin with the current at the top of the loop. I'll call this, we have this DL1 at the top. We know that we have a vector that points from this DL to the point of interest, which I'll call R1 vector. And our magnetic field direction is going to be in the direction created by this dl cross r hat. So in this case, we need dl1 cross r1 hat, right? That is going to be the direction that we need. Now, the easiest way to find this is using the right-hand rule. So if you put your index finger pointing out of the board in the direction of I or DL1, so this is where your index finger should point out of the board. The other fingers should point along R1 toward point P. And if you arrange your hand this way, your thumb should be pointing up and to the right, making a 90-degree angle with R1. And this is what I will call B1 hat. That is the direction of the magnetic field due to my little chunk of current I1 at the top. And what we can say is that the magnetic field due to little dl1, which I will call B1, or maybe dB1, the little bit of magnetic field due to dl1, is going to be equal to some magnitude dB, the little bit of magnetic field due to that little bit of current, and it is going to be in the B1 hat direction, right? So I have some magnitude and I have my direction. So now let us look at DL2, our other little bit of current at the bottom here. Well, DL2 has an R2 vector associated with it, which points straight toward point P from the bottom of the loop. And if we do our right-hand rule for DL2 cross R2 in order to find our magnetic field direction, just the direction again, due to this little bit of current at the bottom, well, our index finger should again point in the direction of I, so that points into the page. So our index finger points into the page. Our other fingers point in the direction of R2 at point P, and our thumb therefore points down and to the right as shown. And this must be the direction of B2 hat, right? The direction of my magnetic field due to this little DL2. And if we think about this, we can also write dB2, my little bit of current of magnetic field dB2, as dB times B2 hat. Now, I know that these two magnetic fields must have the same magnitude, so dB for number 1 and dB for number 2 must have the same magnitude, because if I look at my magnetic field equation, the I is the same for both of them, the R, the radius of the loop, is the same, and Z is the same for both the first point at the top of the loop and the second point at the bottom of the loop. They share all of those values that go into my magnetic field magnitude, and so the magnitude of these two little bits of magnetic field caused by these little bits of current must be the same. So the only thing that varies between these two is their direction. And I know that my total magnetic field due to both of these currents combined I can write as just the sum of those two currents. This means that I can write my total little bit of magnetic field as the sum of these two vectors. And I'm just going to graphically add these two as vectors. I'll begin by drawing dB1 as a vector up and to the right. So this is my dB1 vector. And then I will draw my dB2 vector from the end of dB1. And I know that these two vectors must have exactly the same length because they have the same magnitude of just little dB, and they point in directions such that their y components completely cancel and their x components add like this, and we end up with a total vector, a total magnetic field vector that just points straight outward from the loop with a length which is just the sum of the x components of those two vectors. The y components cancel out and the x components add. So looking back, what we can see is that the magnetic field all along the center of this loop points directly away from the loop if it is on the right side of the loop. We could imagine doing the same thing on the other side of the loop. So if we put our point P here instead, what we would find is that our magnetic field, due to 1, points this way. We would have some little dB1. You can verify this by doing the right-hand rule again and drawing out your R1 and R2 vectors. You would have a dB2 that points this way. And a total magnetic field that points toward the loop here. Now, what this means is that the magnetic field at any point along this axis always points to the right and always has a magnitude given by this expression here circled, which depends on my current, the radius of my loop, and how far away I am from the loop. Now, one thing to consider is that I only did this for two little points at the top and at the bottom, right? I never actually considered any other points except for those two top points. And if you want to find the total magnetic field, you need to consider the entire loop. But the important thing here is that what happens is that the magnetic field due to the top and the bottom, the components, the y components cancel out and you get only an x component. This will happen for any two components that you pick. So say I picked DL3 and then some other DL4 that is directly across from it. I could do exactly the same analysis where I draw my R vectors and I find my R hat, and it would get a bit messy because there's a Z component now because these DL3 and DL4 have Z components in their R vectors. That is, it has to move to get from DL3 to point P, because point P is along the axis and DL3 is kind of up out of the page somewhat, right? If you're looking at this as a 3D loop, you would have to move down into the page as you move from DL3 to point P. So the math would get a little bit messier, but you would find exactly the same thing. That is that the components that are not parallel to this line running through the center cancel out, and the components running parallel to the center add together. So what you will find when you look at a loop like this is that the magnetic field at any point along the center can be given by the magnetic field magnitude here multiplied by the vector that runs along the center of the loop. In this case, it's I hat. So if I had to write down the magnetic field at that point P, I would write mu naught I r squared over 2 times r squared plus z naught squared to the 3/2 I hat, because the vector points directly to the right in the I hat direction, and the magnitude is given by our equation here. The same thing would happen if I did this other point to the left. So now I'll call this distance here from my second point to the center of the loop, I'll call that L. So then the second one, I'll call this point point A. So this is the magnetic field at point P, which was to the right, call that point A. So this would be mu naught I times r squared divided by 2 r squared plus L squared. And it still points, and that is to the 3/2, and it still points in the I hat direction because the magnetic field along that line all points to the right. We can further confirm our ideas by simply drawing the magnetic field lines of this loop. So we know that the magnetic field lines of a loop act like loops of their own, circling the loop in this way, looking like a dipole field, where the magnetic field lines point to the right in this case. So each of these field lines points to the right, out of the right side of the loop, and then into the left side of the loop. Now, all of the field lines above my central point curl up, and all of the field lines below my central point curl down. And there's actually another field line that runs straight through the middle, as drawn by my green line here, which points straight to the right. So it's perfectly centered between the field lines that curl up and the field lines that curl down, and it points to the right. Finally, if we reverse the direction of the current, then we reverse the direction of the magnetic field. And our magnetic field will flow out of the loop to the left here, and our central magnetic field, instead of pointing to the right, will all point to the left. And again, you can find this out by simply doing the right-hand rule as we did at the beginning of the video to see how the magnetic field of the top created by the top and bottom points adds up, and then extrapolate that out to the rest of the loop, realizing that points opposite each other are going to cancel out their kind of perpendicular components, the components of the magnetic field that don't point straight along the loop's axis.